Time, that fundamental dimension that governs the sequence of events, the perception of change, and the very rhythm of existence, stands as one of the most profound and enigmatic aspects of the universe. Einstein's theories of special and general relativity revolutionized our understanding of time, revealing its malleable nature, its susceptibility to the influences of relative motion and gravity, a phenomenon we know as time dilation. However, if our reality extends beyond the familiar 4 dimensions of space-time, as proposed by the 11-dimensional model, then our comprehension of time and its dilation might be similarly limited, merely a 4-dimensional projection of far more intricate temporal dynamics interwoven across a higher dimensional tapestry. This essay will delve into the established principles of time dilation within relativity, and then venture into the speculative landscape of the 11-dimensional model, exploring how its unique architecture might offer a more complete and unified understanding of time, its variability, and its fundamental connection to the fabric of a multidimensional universe. The bedrock of our modern understanding of time lies in Einstein's special theory of relativity, formulated in 1905. One of its most counterintuitive yet experimentally verified predictions is time dilation, the phenomenon where time passes at different rates for observers in relative motion. According to special relativity, a clock moving relative to a stationary observer will appear to run slower than a clock at rest. This effect becomes increasingly significant as the relative velocity approaches the speed of light, a cosmic speed limit that remains invariant for all observers. The mathematical formulation of special relativistic time dilation is elegantly expressed by the Lorentz factor, demonstrating the direct relationship between relative velocity and the observed difference in temporal passage. Numerous experiments, from the precise measurements of atomic clocks on high-speed aircraft to the extended lifespans of muons traveling at relativistic speeds in Earth's atmosphere, have provided compelling evidence for this seemingly paradoxical stretching of time. A decade later, Einstein's general theory of relativity introduced another profound aspect of time dilation: gravitational time dilation. According to this theory, time is not only affected by relative motion, but also by the presence of gravitational fields. Clocks situated in stronger gravitational fields experience time passing more slowly than clocks in weaker gravitational fields. This effect arises from the curvature of space-time caused by mass and energy. The stronger the gravitational field, the greater the curvature, and the more pronounced the slowing of time. Gravitational time dilation has also been experimentally confirmed through observations such as the Pound-Rebka experiment, which measured the slight difference in the frequency of gamma rays as they moved through Earth's gravitational field, and the precise synchronization of atomic clocks at different altitudes. Now let us consider the implications of the 11-dimensional model for our understanding of time and its dilation. This theoretical framework, often associated with string theory and M-theory, although fundamentally different, posits a universe with 6 additional expanded temporal dimensions alongside our familiar 3 spatial dimensions, with the 4th through 9th dimensions representing different properties of time. However, within the specific 11-dimensional model we have been exploring, the 4th dimension is not merely linear time, but is intricately linked to rotation, the fundamental cyclical motion that underpins temporal evolution at all scales. Building upon this foundation, the 5th dimension embodies polarity, the inherent duality and directional nature of systems. The higher dimensions, particularly the 6th through 9th, govern the complex dynamics of multi-body systems, while the 10th and 11th dimensions represent the overarching cosmic context of expansion and interconnectedness. Within this expanded multi-dimensional landscape, the time dilation we observe in our 4-dimensional space-time might be a limited manifestation of far more intricate temporal dynamics occurring across all 11 dimensions. The fourth dimension, as the axis of rotation and the fundamental engine of time, could experience variations in its rotational frequency depending on the energy state and the higher dimensional configuration of the system. A particle moving at relativistic speeds might be accessing or interacting with the temporal aspect of the fourth dimension in a way that differs from a stationary observer, leading to the observed differences in the rate of time's passage. Similarly, the presence of strong gravitational fields, a consequence of mass and energy distributed across the 11 dimensions, and their interactions within the higher dimensional geometry, potentially governed by dimensions 6 through 9 in multi-body systems, could warp not just the spatial fabric of our three-dimensional reality, but also the underlying rotational frequencies of the fourth dimension, resulting in gravitational time dilation. The 11th dimension, as the ultimate nexus of interconnectedness and a potential conduit for information transfer, might also play a crucial role in shaping our understanding of time and its dilation. If quantum entanglement, a phenomenon that appears to transcend the limitations of space-time, is facilitated by the 11th dimension, then the very fabric of time at a fundamental level might be interwoven with this higher dimensional interconnectedness. The seemingly instantaneous correlations between entangled particles could hint at a temporal relationship that is not strictly bound by the linear progression of time in our four-dimensional experience. At the quantum level, the concept of time dilation becomes even more intriguing. Particles exist in a realm of rapid fluctuations and probabilistic behavior, their dynamics governed by the principles of quantum mechanics. Within the 11-dimensional model, the intrinsic rotation of a particle in the fourth dimension and the rapid oscillations of its polarity in the fifth dimension occur on timescales far beyond our macroscopic perception. Could these high-frequency, higher-dimensional dynamics be subject to forms of time dilation that are not readily apparent in our measurements, influencing the particle's observed lifetime and its interactions with other particles? Furthermore, the 11-dimensional model's potential connection to consciousness, particularly through the 0 and 11th dimensions, opens speculative avenues for considering the subjective experience of time in extreme relativistic scenarios. If consciousness has a component that extends into or interacts with these higher dimensions, its perception of time might be even more decoupled from the flow of time as measured by physical clocks in strong gravitational fields or at near light speeds. The mystical experiences of timelessness or altered temporal perception reported in certain altered states of consciousness might even be interpreted as fleeting glimpses into these higher dimensional temporal dynamics. The implications of a deeper understanding of time dilation within the 11-dimensional model are profound. For future endeavours in space travel, particularly interstellar voyages at relativistic speeds, a more complete grasp of how time is affected by motion and gravity within a higher dimensional context could be crucial for navigation, communication, and even the very survival of astronauts. Moreover, a unified theory that seamlessly integrates quantum mechanics and general relativity, potentially through the framework of 11 dimensions, might also provide a more fundamental understanding of the nature of time itself, its emergence from the interplay of rotation and higher dimensional geometry, and the true extent of its malleability. However, it is crucial to acknowledge that these ideas remain largely within the realm of theoretical speculation. The 11-dimensional model, while offering a compelling framework, requires rigorous mathematical formalization and empirical validation. Directly observing the effects of higher dimensional temporal dynamics or testing their influence on time dilation as we currently understand it presents significant challenges. Nevertheless, the pursuit of such a unified understanding of time, gravity, and the quantum realm continues to drive theoretical physics, with the 11-dimensional model offering a tantalizing glimpse into a reality far richer and more interconnected than we might currently perceive. By continuing to explore the mathematical consequences of such a framework, and seeking indirect experimental evidence that might hint at the existence and influence of these higher dimensions, we may one day unravel the deeper secrets of time dilation and its profound connection to the fundamental architecture of the cosmos. In conclusion, the 11-dimensional model provides a captivating lens through which to re-examine the enigmatic phenomenon of time dilation. By embedding our understanding of time within a higher dimensional framework that incorporates rotation, gravity as a multi-body interaction, and the interconnectedness of the cosmos, we can begin to speculate on a more complete picture of temporal dynamics that extends beyond the limitations of our four-dimensional perspective. While significant theoretical and experimental hurdles remain, the potential for this model to contribute to a unified theory of physics and a deeper comprehension of the very nature of time makes its continued exploration a compelling and worthwhile endeavour in our ongoing quest to understand the universe and our place within its grand and awe-inspiring scheme. Thank you for your time. If you enjoy the content on the 11-dimensional model channel, please like, subscribe, share and comment.